In the last lecture, we had introduced the concept of a vector potential for the magnetic field, and it was defined through a relationship which says del cross of A gives you the magnetic field B. What we also did is to say that because of the fact that curl of gradient of any scalar function is equal to 0, the vector potential is not totally completely defined by this equation. So, the curl of the vector potential is the magnetic field, which is of course, a physical quantity, but because it is a vector quantity, vector field, we still have the liberty of choosing what its divergence could be. And we had seen that it is possible always to do so, to have a proper choice such that del dot of A can have any value as we liked. And in particular, we had said that del dot of A equal to 0 is a very convenient gauge, which is known as the Coulomb gauge. So, what we will do today is to continue this discussion of the magnetic vector potential and calculate it in a few cases. The first simple example that we want to do is to calculate the magnetic vector potential for a current carrying conductor, long current carrying conductor, and let us take the magnetic the direction of the current to be along the z direction. This is infinite, and we had seen that there is a stronger relationship between the vector potential and the current density, and I expect the vector potential to be in the direction of the current. So, let us look at what the vector potential could be. So, for instance, if I look at a distance r and sort of try to find out what is the vector potential there, then this vector potential expression A of r is given by the constant mu 0 by 4 pi. And if you remember that if I take a current element d l or d z in this case here, so that this is the distance between the point P where I want to calculate the vector potential and this current carrying conductor. So, this is simply given by, because it is a line current, this is simply given by the current I multiplied by k d z. I times d z in the direction of k gives me the current element on d z, divided by this distance, which is square root of r square plus z square. And because of the fact that my integrals, the z is from minus infinity to plus infinity, now this is what I expect it to be. Now, let us look at what it gives us. So, notice I have to calculate this integral, which is d z over z square plus r square square root, not a very difficult integral to do. If I simply use z is equal to r tan theta, so that d z is r sec square theta d theta. So, this quantity becomes r sec square theta d theta divided by, this is 1 plus tan square theta, that is sec square theta, and so that is r sec theta. So, this is simply an integral of sec theta, which we know is given by log of tan theta plus sec theta. if you put it back into this expression for A after putting in all the constants back, I get mu 0 I k by 4 pi and logarithm of, I have a tan theta plus sec theta, and tan theta as you can see is z by r and sec theta is the square root of r square plus z square. So, this is given by z plus root of r square plus z square. And this has to be evaluated from minus infinity to plus infinity, and this goes to this result diverges. Now, so this does not quite give me the vector potential if I calculate this straight way, and the primary reason is that I have an infinite current element, an infinite current carrying conductor. However, I can do something else. I can calculate the vector potential from the expression of the magnetic field itself. I know by Ampere's law the field at the point r is given by mu 0 I by 2 pi r times in the direction of the azimuthal direction, that is the direction phi, and this quantity is del cross of A. So, what I do is this, I notice this is only in the phi direction, and so if I use the cylindrical symmetry, then I know that I can simply get the phi direction from from the phi component of this, and that is given by d a z d a r by d z minus d a z by d r, and this quantity is equal to mu 0 I by 2 pi r. Now, notice by symmetry I do not expect a derivative with respect to z to survive, because I do not expect A r to have a z dependence, because z is the symmetry axis, it is an infinite thing. So, I expect for all values of z given z, the value of the A r would be the same. And so, that gives me that minus d A z by d r is equal to mu 0 I by 2 pi r, and that tells me that the A is along the z direction. So, A at the point r is along the z direction. This can be integrated trivially to give me what is A z, and that gives me mu 0 I by 2 pi times logarithm of r. And as we have said repeatedly, this is not unique, but I can always add a gradient of an arbitrary scalar function there. So, this is the expression for the vector potential for a current carrying conductor. There is another trick which turns out to be very useful, and that is that we know that I can directly connect or relate an integral of the vector potential with the flux, and that is done this way. Supposing you are to calculate A dot d l, that is the line integral of the vector potential along any closed loop. Now, I can use the Stokes theorem to convert this into del cross A dot d s over a surface whose boundary is given by this curve, and del cross A we have said is B. So, this is nothing but B dot d s, which is nothing but the magnetic flux phi. So, there are situations where it is more convenient to compute the magnetic flux and then use the symmetry to find out what A could be and what A dot d l could be. A typical example, you can see it on this slide here. I am considering a solenoid, and so basically the axis of the solenoid is along the z direction. and these are the turns of the solenoid. Now, notice that if I take a circle of radius z, radius s, such that this radius s is less than the radius of the solenoid, then I have seen that inside a solenoid the magnetic field is constant. So, let us look at inside the solenoid. So, I expect inside the solenoid the magnetic field B to be given by mu 0 n, which is the number of turns per unit length, times the current, and it is along the z direction. So, if I take a circle of radius small r, since the magnetic field is constant, the flux phi through that surface will be given by pi r square times field B, which is pi r square mu 0 n I. But since the loop is cylindrical, a loop is circular, since the loop is circular and symmetry tells me there is no reason why the vector potential should depend upon should vary from point to point on the loop. So, A dot d l should be A times 2 pi r. Notice that I have not talked about the direction of the current, because direction of the vector potential, because I have said that the direction of the vector potential will be along the direction of the current, and in this case the current is in azimuthal direction. So, therefore, this is actually A phi. And that is equal to pi r square times mu 0 n I. This tells me that the vector potential, which has only the phi component, after cancelling out 2 pi, one of the r's and things like that, is mu 0 n I r divided by 2. This picture had that radius as s, but let me, since I have used r, so let me say this is r less than or equal to r. Now, notice one thing, that outside the solenoid the field is 0, but if I take a loop outside the solenoid, my A dot d l, which is still given by outside solenoid r is greater than capital R, which is the radius of the solenoid, and A dot d l is given by 2 pi r times A, which you have seen is along A phi. Now, this is the flux. Now, the flux, there is no contribution to the flux from outside the solenoid, because the field there is 0. So, therefore, what I get is pi r square, but this time capital R square, times the magnetic field, which is mu 0 n I, and that tells me that A phi is given by mu 0 n I by 2 r and times of course r square. So, you notice that the magnetic vector potential with distance r is falling as 1 over r, and inside the solenoid we had seen that it was proportional to r. So, typically the vector potential A phi would do this, that is inside I will have a linear increase, and then of course, there will be a decrease like that. And of course, A only depends upon phi. You can check that del dot of A, since there is just a phi component, you can compute del dot of A by looking up the expression for the divergence in the cylindrical coordinate, and you can show this to be equal to 0. So, we are working in Coulomb gauge. Now, this fact that the vector potential has a non-zero value outside the solenoid as well as inside the solenoid, unlike the magnetic field, which was 0 outside, but had a finite value inside, has been of great use in proving the physical reality of the vector potential itself. And this has been done by, this is actually useful, or these are more a quantum mechanical experiments, but I would point this out here to tell you that the vector potential very much has a realistic origin. And this is done by an experiment which goes by the name Aharonov-Bohm effect. Now, the experiment is very simple. You recall your Young's double slit experiment. So, basically I shine, well, in this case instead of light, I shine a source of electrons, that is a electron beam is shown upon a Young's double slit type of experiments. The Young's double slit experiment is not just restricted to light, it can be done by electrons or any other beam that you feel like. Now, notice that what is done in this experiment is that this is of course the beam of electrons, which is shown on a double slit, and just outside that means between the screen and the slits, I have put in a rather small size solenoid. Now, initially solenoid is there, but there is no magnetic field in it. That is, I am not passing a current through the solenoid. I just do the standard double slit experiment with the beam of electrons. And we know that interference pattern will be seen on the screen. That is because there is a phase difference between the electron wave coming from one of the slits and the other, and that, just like in optics, gives me a interference pattern. Now, what we do next is this, that we switch on a magnetic field, that is, we switch on the current inside the solenoid. Now, and let the electron beam pass through this. Now, remember, because of the fact that the solenoid is extremely small, most of the beam, it has a very small cross section, most of the beam actually passes outside the solenoid. So, in principle, in the limit of an extremely small solenoid, I do not expect this to affect the interference pattern, because when I have a beam of electrons passing through a magnetic field, it is of course subject to a force. But in this case, very insignificant amount of the electron beam passes through that solenoid. But however, what one notices is that there is a phase change, that is, the interference pattern changes. Now, in this course, I will not be able to give you a realistic explanation of why this happens, because it is actually quantum mechanical in origin. One can relate that the fact that the region in which the electron beam is passing through, in that region the vector potential is not equal to 0. And this has an effect on the electron wave's phase. And this phase difference shows up in the pattern that you actually see on the screen when you switch on the magnetic field. So, this is something which is good to keep in mind, that what we had thought to be a mathematical artifact actually has a reasonable physical effect which one can actually demonstrate. But I warn you, these are difficult experiments done with quantum waves. We continue with our examples of the vector potential. So, let us calculate the vector potential corresponding to a situation where the magnetic field is constant. This is a very useful thing, because very often in an experiment you deal with constant magnetic field. So, let me write down constant magnetic field to be B. At this moment I am not talking about a direction. So, I claim that the vector potential A is given by this expression B cross R by 2. This is, of course, as we have said repeatedly, that this is one of the possibilities. So, notice that I know this is a vector algebra. So, del cross of u cross v, where u and v are two vector fields, is given by u del dot v minus v del dot u plus v dot del u minus u dot del v. This I am not going to derive it, but just be careful, these are all vector expressions. So, remember when you say del of v, it actually means three things and gives rise to del of v x, del of v y, del of v z, and then that vector is to be dotted, and so because of that each one of these is actually a vector. So, notice that I am claiming that A is B cross R by 2. In other words, I am saying that if you take del cross E, it should give me B. So, let us check why. So, del cross B cross R by 2 notice there is a half, of course. In this case, identify u with B and R with V. So, what I get is B times del dot R minus R times del dot B plus R dot del of vector B minus B dot del time of vector R. Now, notice we are talking about a constant magnetic field B. So, therefore, that gives me del dot of B equal to 0. So, this term goes away. I know del dot of R, which is divergence of R, must be equal to 3, and similarly R dot del B, because B is a constant, that is equal to 0. So, I need to calculate what is this term. So, this is also equal to 0. So, I need to calculate what is B dot del of R. So, remember that the way to understand this is B dot del is to be written as B x d by dx plus B y d by dy plus B z d by dz, and vector r is of course I x plus j y plus k z. So, this is equal to d by dx of this quantity gives me simply I, because only d by dx of x is important. So, that gives me I times b x. Similarly, d by dy gives me b y. So, that is j times b y, and of course, k times b z, which is nothing but vector b itself. Del dot of r, divergence of r is equal to 3. So, that gives me 3 b, this is the minus b. So, that gives me 2 b, and of course, there is a factor of 2 here. So, that tells me that del cross B cross R by 2 is indeed the vector B as it ought to be. So, this tells me that an expression for the vector potential corresponding to a constant magnetic field is given by B cross R by 2. This is a rather important expression to remember. Now, let us look at a Coulomb gauge, that is del dot of A equal to 0. So, in Coulomb gauge del dot of A equal to 0, suppose B is in z direction. Let me take B in z direction. You can immediately see I can write the vector A, which is B cross R. So, since it is B cross R's components, now you can check that this is given by one of the possible expression is, for example, minus B y by 2 B x by 2 comma 0. That is, the x component of the vector potential is proportional to y, y component is proportional to x. You can check that del dot of A is equal to 0, and del cross of A will give you vector B when calculated. But this is not the only expression possible. As we had seen, for instance, you could do this, you could be B y 0 0. Remember, we are only interested in del cross A's z component, because I know that I wanted the magnetic field to be in the z direction. So, this is nothing but d by dx of B y minus d by dy of B x. So, take the first expression d by dx of B y, B y is B x by 2, so that gives me B by 2. d by dy of B x, B x is minus B y by 2, so that gives me another minus B by 2, so that is B. Alternatively, I have a minus B times y, this is 0, and minus minus plus d by dy of that is B. So, either of these expressions or many other possible expressions can be shown to correspond to the constant magnetic field. This is, as I pointed out, this is a rather important relations. Let me take vector potential corresponding to a current sheet. We know that if you have a current sheet, you can basically it gives me linear current, because there is no cross section actually. You take a cross section, put it to be equal to, let it go to 0. So, what I get is a linear current density, which is measured in ampere per meter. So, I have this linear current density as k times I, and the magnetic field corresponding to such a current density can be easily computed using the Ampere's law. So, that gives you that the magnetic field is constant both above and below. It points, as you can see, because if I point my thumb along the direction of the current, the direction in which my fingers curl, that gives me the direction of the magnetic field. So, in this particular case, that what I notice is this, that if this is my x direction and this is then the minus y direction. So, the expression for the magnetic field for a current sheet is given by minus mu 0 by 2 linear current k along the z direction, and is plus mu 0 by 2 k along the j direction. This is above the plane z greater than 0, and this is below the plane for z less than 0. Now, I need to calculate the magnetic vector potential corresponding to this. So, let me do one of them only. Let me just calculate it for z greater than 0. Now, notice this field is constant, and just now we have seen that the vector potential corresponding to a constant field is given by half B cross R. So, therefore, A is equal to A above x y z is given by half of B cross R, and since a cross product I write it in terms of a determinant which is I j k. I need components of B in the next row. Components of B is only along the y direction. So, it is 0 minus mu 0 k by 2 0, and of course, component of R which are x, y and z. This is rather easy to calculate. This is equal to half I times, you can see, minus z mu 0 k by 2. So, it is mu 0 k by 2, which makes this 2 into 1 by 4, mu 0 k this times z times I. And then there is no j component, but there is a k component, and that is equal to plus, this is a minus sign there by determinant, plus mu 0 k by 4, this times an x, this time an x and a j. You can easily check that corresponding to z less than 0, the expression will be almost identical with this minus sign becoming a plus and this plus sign becoming a minus. So, therefore, one of the things that you notice is the following, that if you are looking at any component, normal or the tangential component of A, that is actually continuous across the boundary, because both these expressions they are continuous across the boundary. My next example is going to be a circular current loop. It is a little tricky, but is also a lot more important because of its utility. So, let us return back to the expression of the vector potential at a point r, at a position r, which is given by mu 0 I by 4 pi integral of d r prime. Remember, according to our usual convention, the primed quantities are the source, that is where the current is flying, and unprimed quantity, namely r, is the position at which I am calculating the vector potential or magnetic field or whatever you have. So, I have a 1 over r minus r prime. Now, what I am going to do is to assume that my current distribution has a smaller dimension compared to the distance where I am trying to calculate the magnetic field or the vector potential. So, that I will assume this r is greater than r prime. So, what I will do is, while doing electrostatics, we had seen 1 over r minus r prime had an expansion, which is mu 0 I by 4 pi, loop integral remains. Since r is large, I will take this as sum over L is equal to 0 to infinity. I will pull out 1 over r to the power L plus 1, and then I have r prime raised to the power L and P L cos theta. This expansion in associated Legendre polynomial is something which we had done earlier. Now, what we are going to do is this, that let me retain only some lowest powers of these. So, for example, I can write down retain L is equal to 0 term first, mu 0 by 4 pi. If I take L is equal to 0, this is r prime raised to 0 is 1, and you have got an 1 over r there. So, let it come out, and a loop integral of d r prime. I need a dr prime back here. The second term is mu 0 I by 4 pi, L is equal to 1 is r square, loop integral of r prime to the power L, which is just r prime, P L cos theta or P 1 cos theta is just equal to r prime cos theta and dr prime. Notice this term is integral of a vector in a closed loop. So, it is equal to 0. And so, the first leading term that we need to calculate is this term, which is mu 0 I by 4 pi r square integral of, remember that theta is the angle between r prime vector and r vector, but I have just r prime cos theta there. So, what I will do is to write this as the angle between unit vector r with r prime vector and dr prime. So, this is the formal expression and I need to calculate this. So, let me write it again. There is a little cumbersome mathematics, but on the other hand fairly straightforward. Mu 0 I by 4 pi r square loop integral of r dot r prime dq dr prime. Now, what I am going to do is this. I am going to express this loop integral in a particular fashion, and this particular fashion is to express it as a sum or difference of two quantities. One of them is a perfect differential, and I know if it is a loop integral of a perfect differential, it is equal to 0, because it just returns back. As you know, the finite integrals only depend upon the endpoints. So, to do that, I notice this. If I look at r cross r cross r prime cross dr prime, I will alert one thing here, that you see this is a dr prime vector. In other words, this is a change in r prime, that is a small change in the vector r prime. Now, this you use the standard b a dot c minus c a dot b, which is the standard expansion for a cross b cross c. So, that is equal to r prime vector multiplied by a dot c, which is r dotted with dr prime, minus dr prime vector and r dotted with r prime. Now, I know that if I take a differential d of r prime times r dotted with r prime, I would get, remember the vector r is a fixed vector. So, what I am going to get is dr prime times r dotted with r prime plus r prime times r dotted with dr prime, because the differentiation is only with on r prime. Now, if you combine these two expressions, in other words, I am going to replace this r prime r dotted with dr prime through this minus that. So, what you get is that dr prime times r dotted with r prime is equal to minus a half. You can check that one of the term comes twice, and that gives me a factor of 2, r cross r prime cross dr prime plus half of this differential r prime r dotted with r prime. Now, remember that I have to put this inside that integral, and that will make this term vanish. So, a of r for the circular current loop to the order of expansion that we have been making, that is retain the L is equal to 1 term only, is mu 0 I by 4 pi. Now, remember that I had a unit vector there. Now, I could write it as by bringing in another r in the denominator as vector r, and then I can use this expression. So, I get 4 pi r cube times minus a half r cross, r is a constant vector. So, it comes out, and the loop integral is simply r prime cross d r prime. So, this is an expression for the vector potential. But notice what is this? This quantity here along with the factor half is nothing but an area. It is the area of the loop, circular loop. Now, if this is the area of the circular loop, that multiplied with that current is in the direction of that vector area is what we define as the magnetic dipole moment. So, the magnetic dipole moment of a closed circuit is given by the current multiplied by the area vector, and that is given by this expression there. Half of this is the area, and so therefore, if you look at this expression, you will get A of r is given by mu 0 by 4 pi, I is taken care of in the definition of the magnetic moment, and I get m cross r, that minus sign I have taken care of by reversing the sign of the order of the cross product. I get m cross r divided by r cube. Now, this is the general expression for the vector potential for a small current loop. Small I say because I have done expansion in spherical harmonics and retained the first order term only. Okay. Now, I can now calculate from this the corresponding expression for the magnetic field. Now, recall that earlier also we had done, we had calculated the magnetic field due to a circular current distribution, but we were only able to calculate the magnetic field on the axis of the circular coil. So, what we are going to do is this. Since to the order of approximation which we have used, this is a general expression. So, B of r due to a magnetic dipole is given by mu 0 by 4 pi del cross m cross, I will take the second vector as r by r cube, and del cross, and that I will use the following. Remember that vector m does not depend upon position r. So, therefore, there is no differentiation etcetera comes for the vector m, but this sort of acts like a scalar. It is not really a scalar, it is a vector, but it acts like a multiplying factor for the del operator. So, this gives me m times del dot of r by r cube minus m dot del r by r cube. I leave it to you as an exercise because we have several times done this calculation, divergence of a scalar times a vector. This you can easily calculate, and this gradient calculation is something which I did some time back, that it is to be what is meant by gradient of a vector, that is I have to take component wise and do it. And you can show that this gives me mu 0 by 4 pi 3 times m dot r divided by r to the power 5, r to the power 5 because there is a del dot of 1 over r cube being taken, and there is a, notice there are 2 r's there. So, there is a 1 over r cube as again as before, and that is minus m by r cube. That is a rather well known expression, and this is the coordinate free form for the expression of the magnetic vector potential, magnetic field due to a current loop. Having done this, I next go over to a discussion of the boundary conditions which are applicable both for the magnetic field and for the magnetic vector potential. Remember, we did similar things with the electric field, but this time I have slightly different equation. So, therefore, I expect some changes. So, let us look at the condition for the boundary conditions on the magnetic field itself. So, this is interface, arbitrary interface between the medium 1 and the medium 2. Now, I know that del dot B equal to 0, alternatively I have B dot d s equal to 0 over any closed surface. Now, what we are doing is this, that if I have this figure, I take a Gaussian pillbox. I take a Gaussian pillbox of height h, which I will take it as negligible, and this is negligible means it is small compared to, let us say, the radius of the pillbox. The outward normal on this surface is that way and on that surface is this way. So, the B dot d s, there is no contribution from the sides because I have taken h to go to 0. If I take capital S to be area of these end caps, then B dot this 2 is for the medium and not to be taken as a square. So, I get area times B 2 n minus B 1 n minus, because the direction of the normal is, I have to take one direction for the normal, but here the outward normal would have been that way. So, B 2 n minus B 1 n is equal to 0. Cancelling out the s, I have B 2 n is equal to B 1 n. So, let me write it down. The normal component of the magnetic field is continuous. Now, remember that in Coulomb gauge I had del dot of A is equal to 0, which is identical to this expression there, that integral B dot d s equal to 0. I can have integral A dot d s equal to 0 using the divergence theorem. So, just the same way I can write down A 2 n is equal to A 1 n. In other words, the normal component of the magnetic field as well as the normal component of the vector potential are continuous across a boundary. Now, the tangential component poses a little more tricky situation, but let me go through this. What I do is, I have this boundary and I take a rectangular loop of height h, which will be taken to be small compared to these distances. And what I will do is to calculate what is integral of B dot d l. We know that integral of B dot d l is mu 0 I. The current I is J dot S and the surface area is L d h. So, what I will do is this, that is in this picture I have shown a direction which is S unit vector S, which corresponds to this loop, and that is, if I take the loop in the direction of my thumb, then the direction in which the finger points for the thumb points is the direction of this normal. This is not to be confused with the direction of the normal to this surface. In any case, look at this, that then I get the B 2 t minus B 1 t into L is equal to mu 0 L k dot S. Now, what this is telling us, which we will do repeat next time, is that the tangential component of the magnetic field has a discontinuity when there is a current, surface current across the two media. This is very similar to what we did earlier for the electric field case, and we found that the normal component of the electric field had a discontinuity when I had a charge density on the surface. We will return back to these boundary conditions in the next lecture.